of polymer mixture.
Okay, so thanks. So after arranging myself, I first of all want to thank the organizers for inviting me to this very interesting event, and I must say I can only emphasize and underline what Barbara has already said, that this meeting has been great fun meeting and talking to people, and I'm also very impressed by the way this subdued and understated building really fosters communication between scientists. I think very few architects get it right, and this one really did. So today I'm going to talk about actually a cluster of ongoing work centered around an application, which I've shown here. This is the production of organic solar cells, and this is nearly by definition an application involving complex fluids. So what typically happens in these experiments, and this cartoon is taken from one of the experimental groups in the UK, Harriet and Jones, is that people mix two polymers, the donor and the acceptor. So instead of having differently doped silicon, for example, as in conventional cells, you will have two different types of polymers. You mix them together in a common solvent. As long as there's enough solvent, these two will remain mixed. You put them onto a spinning disk with a substrate. Centrifugal forces will spread out the film. You have evaporation, and eventually, as the solvent depletes, the two constituents will separate, for example, into a bilayer situation. And then you have subsequent instabilities, de-wetting instabilities, Marangoni instabilities, that change the interface and may lead to breakup. The key for the operation of these cells is to have a control on the morphology. So on the one hand side, you want to typically have a tortuous interface, because that's where the charge separation happens from the exciton state, which arise from the impact of photons. On the other hand, you want to make sure that the polymer layers, the two polymers, are connected to the proper electrodes to avoid short circuiting or islands where no charges can be extracted from. So in most of the experiments which are done to understand actually the morphology that arises, the polymers that are used are typically not necessarily the ones used for the organic photovoltaic cells, but kind of for fundamental studies, polymers such as polystyrene and PMMA. And depending on basically all the parameter setups and the type of the polymers, you can get various different morphologies. So one configuration that happens in particular with PS and PMMA mixtures is that you get a stratified bilayer, and it is conjectured, and there's some experimental evidence that you get Marangoni effects, which lead to the corrugation of the interface boundary. Or you can get either subsequently or right from the beginning types of spinodal de-wetting or decomposition into stripes. Now, as I said, all parameters, experimental parameters can play a role, such as evaporation rate, spinning rate, and most of the progress has actually come from just doing large series of experiments. To put a bit of theory into this, we necessarily have to break this problem into bits and look at these bits in a simplified setting. So in this talk, I will look at three aspects. First of all, the question how you control the evaporation to avoid things like skin formation. So you want to remove the solvent in a way that the gradient across the film remains small. So you don't want to have a very inhomogeneous removal of the solvent. The second question is, how do we deal with the Marangoni instability? Can it arise, and how can we analyze it in a setting where, due to evaporation, the base state slowly changes? And then, as an alternative mechanism, can we have a breakup of bilayers due to the confined geometry, and how does the confined geometry lead to a separation into bilayers in the first place? Okay, so let me start with the spin coating. So spin coating is a rather interesting process because it produces a flat film. That's not quite as obvious as it seems. If you think of it, the centrifugal forces which drive the process increase linearly with time, and so does the flow, which means the gradient of the flow is spatially constant, but not constant in time. And that means if you have a flat film to begin with, this film will decrease with a constant rate, even without evaporation. And it was shown by Emsley in '58 that even if you start with a blob, this blob will eventually spread out into a film, and that film decreases as the material gets propelled out by the centrifugal forces. So there's a clever interplay between the forces and the Poiseuille-type flow, which creates exactly these flat films. In '78, Meyerhofer added evaporation, and in '89, Burnside included the effect, Burnside et al. Included the effect of diffusivity that depends on the concentration exponentially strongly on the concentration of the polymer or the solvent, and similarly for the viscosity. And this is essentially the model they looked at. They did some numerics for it, and we explored its the full range using some asymptotic techniques. So as I said, because everything remains flat in the spin coating system, you can have a one-dimensional model. And that's what you see at the top. So you have a convection diffusion equation for the polymer concentration or polymer volume fraction phi. On the right-hand side, you have the diffusive term, and the convective term comes from the normal velocity component, which in turn can be obtained from the horizontal velocity component just by mass conservation. And that gives you the expression in the second line. Boundary conditions are at the bottom, no flux of the polymer, of course, and the interesting stuff happens at the top. So you have evaporation, and in this case, the law you use for evaporation is similar to what you would do for Newton-type cooling for the heat equation. And the reason is that with spin coating you have a constant air flux, which produces a Robin-type condition at the top that depends essentially on the rate, on the spinning rate. So this evaporation leads to a modification of the kinematic condition, which is the first boundary condition up there. It also creates the gradient in the concentration, which is the second condition. And that's already all you need for this problem. You've got initial conditions, which is a flat state of thickness normalized to 1. And the model incorporates in two places the diffusivity and the viscosity dependence depending on the concentration. So you see the nonlinear contribution up in the first equation, and viscosity creates the factor in the integral. There are several non-dimensional parameters in the problem, the key ones being epsilon and delta. Epsilon measures the relative importance of diffusion compared to the advective time scale, and delta measures the importance of evaporation compared to the advective time scale. So small evaporation means small delta. It is kind of what you expect is that the question how homogeneous the film dries or evolves in terms of the concentration or volume fraction would depend on the relative size of delta and epsilon. And that is true, but the exact details are actually quite complicated. So if you go through the asymptotics, you find that there are at least 3 regimes depending on the relative magnitudes of epsilon and delta. And each of these has up to 3 time regimes with different asymptotic structures in the spatial direction. The upshot is that if you have, for example, large evaporation, so delta is, the evaporation is much larger than the small parameter which determines diffusion, the relative importance of diffusion, then you get very strong, then you get a separation into an inner and an outer layer with very steep gradients. So here you would expect that because in the inner layer, which is at the top surface, the concentration reaches basically the maximum 1 very quickly, that this that here you would have a skin formation, a very inhomogeneous distribution of the polymers. The same holds true for medium evaporation, although the big catastrophe happens a bit later. And even with small evaporation, there can be relatively strong gradients, even though the asymptotic structure is more favorable. And it turns out that in one of these spatial regimes, you can still have a strong gradient unless you impose a further restriction, which is just indicated in this diagram. So you need to make delta even small compared to this epsilon to the 3/4 with a factor that depends exponentially on gamma, and gamma controls the degree to which diffusion depends on the volume fraction. So only if evaporation is really small, the distribution remains approximately constant. Okay, so that's good and bad news. Bad news is you can't do things too quickly. The good news is if you do them slowly enough, then you can control these gradients. Now let me go to the second aspect, which is what happens if we still have a gradient, but we also have this bilayer structure which emerges from the phase separation. So now we are back to the situation where we have a solvent and 2 polymers. This is again the cartoon I showed in the beginning, and the 4th picture down there indicates the corrugation, which are by conjecture coming from Marangoni convection effects. Now if you look at the top and you look close to the axis of rotation, you see this structure, and you can imagine that this structure there is somewhat reminiscent of Marangoni type convection cells. So this is some evidence there could be Marangoni convection, and there is some quantitative evidence in these papers. So we thought, okay, let's look at this in more detail, but let's simplify the situation. So instead of using 2 layers, we will only use 1 layer, and instead of looking at Marangoni effects or surface tension gradient effects at the internal layer, we will look at surface tension gradient effects at the upper layer. And for this situation, there are interestingly also some experiments, and not too many, quantitative ones, but one that was published quite recently for a system which involves polystyrene and toluene. And you can see that without spinning, that's another simplification, justified in part by the fact that even spinning has a zone where there's no shear flow. So without spinning, you see these nice convection cells if you look from the top. Okay. So this is the basic picture. We have a fluid and a free interface. We will neglect deformability of this interface. We will neglect spinning, and we'll restrict ourselves to a 2D picture, so there is no y-coordinate in this problem. And the thing we want to focus on is how do we do the stability analysis in a situation where the base state changes over time. So let's go back to the basic equations where we use the Stokes equations for the bulk together with incompressibility and couple it with a convection diffusion equation, in this case for the solvent, C. We have again no impermeability and no slip at the boundary, and at the free interface we have an evaporation, and we still use a very simple law for the evaporation rate, which is similar to what we did in the spinning case. And the Marangoni forces, i.e. the dependence of surface tension, introduces the shear stress, which is down here in the 3rd boundary condition. We start with a flat interface and a well-mixed state where with an initial solvent concentration Ci. There are three non-dimensional numbers in this problem. Beta, which is the initial concentration normalized with the density. Delta is a measure for the evaporation rate as compared to diffusion. So more or less, it's closer to the meaning, I think, of epsilon in the spinning case. So we will keep evaporation small, but still maintain a sizable Marangoni number by assuming that the other parameters in this problem lead to sizable surface tension gradients, even if there's just a modest concentration gradient arising from delta. So this is the limit we want to look at. So first of all, we look at the base state, and it turns out that if we neglect the x dependence, we also get a solution where u and p are both 0, and the concentration is governed by a diffusion equation, plus a contribution from the evaporation at the top. So on an order 1 time scale, what happens is that when you start with a well-mixed state, the boundary layer where you get depletion propagates through the layer. On this time scale, the film thickness doesn't change at all. It's more or less constant. And the concentration gradient builds up. This is what the second diagram shows. So you see that you start with essentially 0 difference between the top and the bottom. And at an order 1 time scale, you reach a certain maximum. That means the concentration gradient has penetrated the layer, and then it remains more or less constant. On a long time scale of order delta to the -1, the concentration gradient then remains constant, while the film thickness slowly decreases. And at the end, when the solvent has basically entirely evaporated, the concentration goes back to 0 again. We are interested in understanding the stability in this period where things change slowly, the base state changes slowly, and we have a sizable concentration gradient. So let's start with the linear stability analysis by perturbing the base state. So we introduce a perturbation that contains all lateral wavelengths to the time-dependent base state. We linearize the problem. It turns out that the velocity components can be reduced unsolved to so that in the end you only have a single equation for the concentration profile, and the effect of the velocity comes in through this term, which also contains the dependence on the base state. Because the base state depends on time, even on a slow time, it still is time dependent. You can't just go ahead and do the normal, the usual normal modes analysis at this point. So the question is, what do we do then? So there are two things that can be done. You can either freeze time and do a linear stability analysis and look at the eigenvalues. Now the normal modes approach works because you basically ignore the time dependence. The second method is you look at the so-called amplification method, and you basically introduce an arbitrary perturbation for a given fixed wave number. You solve the linearized problem numerically and then track the amplification. This is a bit like what Barbara did in her talk. The first method has the advantage that it appeals to something we are all familiar with from conventional linear stability analysis, which is eigenvalues and change of sign of the real part of eigenvalues. The second method is much more universal and gives you the quantity you're looking at, namely the amplification of the perturbation, and it also does not really depend on the slowness of the base state. The question is there any way to connect these two in the case where the base state only evolves slowly? And that's what I want to look at. So various combinations of these methods have been looked at for different problems. I want to emphasize in particular Mahrafi, who looked at the problem which is closest, or actually a superset of what we're looking at here. So in his model, this is Mahrafi and Collinet, they looked at a case where they have basically all types of convection, density-driven convection, either coming from compositional effects or from temperature effects, and also Marangoni effects, and they mainly used the frozen mode analysis. Okay, so the idea is, of course, that these frozen modes, these eigenvalues, should tell you something about the amplification, and to give you an indication of how the connection might work out, let's look at one example of a perturbation. So what you see here in the upper left is basically a stability diagram for the frozen mode case, and in this case the problem essentially reduces to the classical Marangoni problem, which was investigated in a whole slew of publications since Pearson started this in the 50s, I think. So what you see here is the solid line, which corresponds to the stability transition for the initial experimental parameters. So if you see the star over there, that is a specific choice of the wave number, k equals 1, and a Marangoni number which is above this line. So the frozen mode eigenvalue has a positive real part. It's actually real, so it's just a positive real eigenvalues. And this would indicate instability. As time goes by, the system parameters change. The stability threshold goes up as the system becomes more stable. And at some point, this star is on top of the line and eventually below the line, the dashed line up there. So here the eigenvalue is negative and the system should be stable. We now look at what the amplification method tells us. So we track the fate of the perturbation. You see that initially the perturbation grows until it hits a maximum at t equals 23 and then decays. And if you compare the two images, you see that t equals 23 is exactly the moment when the eigenvalue changes sign. So there is a connection between the two, and you can tease this connection out by doing a multiple scales analysis, which is a bit tedious, so I will only show you the final result. What the stability analysis essentially says is it gives you an expression for the evolution of the projection onto the L eigenfunction. So let's set L to 1 and assume we're looking at the eigenfunction that corresponds to the top eigenvalue, the eigenvalue that would determine stability. The first contribution over here is simply an exponential, but instead of having the eigenvalue multiplied with t in there, what you do is you take the eigenvalue and integrate it in time. The eigenvalue is constant because the base state is perfectly constant, and this reduces just to the familiar formula, eigenvalue times time. What is also interesting is that you can now get corrections. So one correction, and this can be relevant, for example, if the eigenvalue is relatively small, close to the stability threshold. This correction is essentially the projection of the time derivative of the first eigenfunction onto itself. And with this combination, you get a fairly good approximation of the amplitude. In the case where the eigenvalue is relatively large, you can forget about this term, and you just have to integrate the eigenvalue in time to get a decent approximation for the amplification. There are other corrections which come into play, and the interesting thing here is that in addition to having factors of delta, which is the principal small parameter, you also get terms which depend on the inverse of the distance of the eigenvalues. So what this method also tells you is that when eigenvalues get close to each other, then the simple connection between the eigenvalues and the amplification can break down, and that's where you have to think about more subtle methods to tease out the information from the frozen mode eigenvalues. And the quality or the assertions coming from a frozen mode analysis have to be taken with some care in this situation. Okay, let's go for the third part. How do we get these bilayers, and can the confinement itself drive a structuring of the interface, even without hydrodynamics and without diffusion? I actually forgot this transparency here, so I wanted to make one comment. We compared these results with the experiments by Basu and Rabi, and it turned out that there is good agreement for thicker films. So both the experiment sees convection rolls, as well as the theory we developed indicates that there should be an instability. If you take thinner films and you get close to the stability threshold, there are situations where the theory predicts stabilization while the experiment still sees the rolls. And even in a case where the experimental parameters are create a Marangoni number below the stability threshold, you still see the convection rolls. So apparently there is either some oversimplification in the model, or this range still has to be considered in more detail experimentally. So one thing we did to expand the model was done by my DPhil student Matt Hennessy. So he also included the effect of deformable surfaces. But as far as I remember, this wasn't enough to really close the gap. So there is still some either experimental or theoretical work to do. In terms of the experiments which we started with, the fabrication of solar cells, we would of course like to get back to the two-layer situation. But yes?
I mean, you have both ways that go first up and then down.
Yes.
I mean, that's all purely linear, right?
Yes.
So could not the nonlinear evolution kick in of the, let's say, the modes that you see first, and then sort of overcome what you see in the linear modes later,
right,
or something like this?
This is true. I mean, this analysis is linear. So the kind of the philosophy behind it is, if you want to get into the nonlinear regime, you need to have a certain minimal amplification. So what we essentially did is we said, okay, if we don't get at least an amplification of a factor of 10, we won't. I mean, this is not enough to really excite any nonlinearity. You can argue about that. Now, the point was, even if you say t to the 0, no amplification is enough. There were few data points which, right from the beginning, if you take the thickest film, the most unstable set of parameters you can take, it's still, the theory, just the eigenvalues predict stability. So no, there will be no growth there. And there, I think it's a bit, you're basically below this black line right from the beginning. So that was a bit puzzling. Yeah. We ignore nonlinear effects, but I don't think, and that's a bit the point here, you can really, assign it to that problem here. But we can discuss it. I think there are also experimental issues there. Okay. Oops. Oh yes. So now for the third part, we have if we look at the initial situation just as the phase separation, we essentially have a confined situation. We have a wall and a free surface, and within this thin film we have the initial phase separation. So we're basically looking at something we would model with, say, some version or extension of Cahn-Hilliard plus the presence of walls. Now, I think there's a whole slew of publications going back in particular to Binder and Puri and Binder. Binder, I think, started in the 90s, and Puri and Binder produced a bunch of papers on all kinds of variations on these themes. So this here is taken from one of their publications where they essentially have one wall, include some type of surface energy, and then look at the situation where they get spinodal decomposition. So you get the separation of the phases, you get coarsening, and because the walls attract one of the two phases, you get a layer at this wall, and this acts as a recipient because it's the place with the lowest curvature, so coarsening will predominantly act towards this layer, and you eventually wind up with a thin film. Now the question we asked is, let's assume we have a bilayer situation, And let's assume there may be some surface energy at the wall. So instead of having just one wall, we will have now two walls. Again, a simplification compared to the experiment because we replace the upper free boundary by a second wall. We start with a bilayer situation. And if the surface energy is not very strong, then the following should happen. If we poke a hole up here, so we let the gray layer touch the upper wall, we have a contact line. This contact line should recede because it shortens the interface between the two. You get an inverse bulge, a dip kind of, which hits the lower surface. That's where the top layer now hits the lower wall. You get a new contact line. Now the gray layer recedes, produces a bulge, and the process should repeat itself in a nice patterning process. Question, of course, still remains, how do you get into this metastable situation? Well, we thought let's look at a Cahn-Hilliard model for this problem and try to follow it through these two stages. So this up here is the usual Cahn-Hilliard equation with the order parameter, some type of volume fraction, for example, coupled to the chemical potential, which is composed of the gradient dependent part, which here becomes the Laplacian, of course, and the bulk part, which is just the normal double well potential. It turns out that it is useful or necessary to control this double well potential by a parameter chi. In the simplest setting, this could be temperature, if we think of alloys, for example. T equals 1 would correspond to the critical temperature, and this means chi is 0. That's exactly the borderline between a double well and a non-double well potential. At the walls, we have no flux, and we have to impose some sort of surface energy. Now, Puri and Binder typically use the first two terms in the Taylor expansion and other types of surface energies. Here we use this quadratic combination because you can make your life a bit easier when you get to the point where you want to determine contact angles. So this is a bit artificial. The exact choice doesn't really matter as far as we think. But it makes our life a bit easier because if we choose these parameters judiciously, we can get a slightly easier expression for the contact angle, which will be relevant once we look at the opening of the holes. We start with a 50-50% mixture, which means phi is 0. So plus and minus 1 are the fully separated phases, or rather, we have a dependence on the temperature. So if chi is 1/3, chi naught is 1/3, then the two equilibria, the stable equilibria, are at plus and minus 1, and the 50-50 mixture, which is highly unstable, of course, corresponds to 0. Okay, let's look at some simulations. So, So what you see here are some simulations done by my DPhil student Matt Hennessy. You have an upper and a lower wall, and we start with phi equals 0 plus some noise. There is a slight bias in the walls, so the walls are antisymmetric with a bit of surface energy. So the effective contact angle would correspond to about 85 degrees. 90 degrees is what you get when there's no surface energy. The perturbations grow and coarsen, and you immediately get stripes. So this is what happens when you just choose a temperature that's well below the critical temperature. You just get spinal decomposition, and that wavelength controls the pattern, which turns out to be stripes. So there's no transition through the metastable state. So what you can do is you can do the cooling more slowly. So this is the same setup, but instead of jumping into the 1/3, we start at 0, which is at the critical, with chi, which is at the critical temperature, and then we lower the temperature slowly. And what you see is that the surface energy creates a thin boundary layer which attracts the two phases. And if you cool slowly enough, you eventually wind up with a bilayer situation. So there's one way of doing this. I just came across a paper by Puri and Binder, which quite interestingly looked at a similar situation. So after they've published 12 or more publications on this, we kind of converged on the question of what happens between two walls. And their suggestion is you could also start with a non-constant gradient, and this would produce the necessary bias to get you directly into the bilayer situation. I haven't checked that in detail, but that might be a different scenario that could also be relevant for the experimental setting we started out with. Okay, now we've got the bilayers, and we want to see what happens when we punch the holes. In this case, it's a bit more convenient to go back to a sharp interface model. So we do the usual expansion, sharp interface limit expansion with an outer and an inner problem. The inner problem provides the boundary conditions for the outer problem, which in turn just turns out to be the Mullins-Sekerka problem. So the chemical potential is governed by Laplace's equation. At the interface, the value imposed is proportional to the curvature. This fixes the solution for mu1, and the jump in the gradient then drives the evolution of the interface. The quantities which appear, for example, sigma, can now be obtained by essentially solving the inner problem. So they come directly from the bulk-free energy. The same limit also gives you an expression for the contact angle, which is essentially the expression you get that I think Kahn already had in his paper 1977. And this limit can be also made rigorous, and that was done in 87 by Modica. So what we're going to do is we want to simulate this sharp interface problem with these contact angle conditions. Now, coming from Occam and having worked on thin films, I can't help but use lubrication theory. You have this long aspect ratio, at least in the case where the contact angles are small. So you do the usual expansion, and you can reduce everything to an evolution equation just for the interface profile H. And that is essentially a fourth order heat equation, plus the boundary condition. So now the contact angle has been normalized to 1. And in the far field, H is 1 and Q is 0. So no flux from the far field. So that's quite simple to integrate numerically. You start with this jump profile, which is the red dashed line. And you see that if you have a contact line there at the edge, it retracts. You get this ridge, and the ridge grows and grows and grows. Two things will happen. Either the ridge hits the upper wall. So in our 50-50 setting, this wall would be located at 2, and that is what would happen. If you don't have an upper wall, so for very asymmetric mixtures, you could think of a situation where you first get pinch off over here. So instead of getting stripes, you would get an array of droplets. Let's focus on the stripe situation and compare the lubrication result, which you see up here. So in this case, the contact line is again at the top wall. It recedes. You get a dimple which hits the lower wall. Now the red-blue contact line recedes, and the blue phase ruptures the red phase at the top, and you get this cascading effect. You can also do this with a phase field model, and you see that there is relatively good agreement between the two models, despite the fact that we made the comparison for 50 degrees, which is not in the lubrication limit. So there are limitations on the practicality of a phase field model. So if the student wants to get done before the end of his thesis, you have to use not too flat contact angles, which would be the ideal situation for a good comparison. And of course, when you go to the 85 or 90 degree case, so when the wall surface energy of the wall is relatively weak, you have to use the phase field model. But again, you get this situation where you get successive ruptures and retraction of the contact line, and then a formation of the ridge, which then creates the next rupture, and you wind up with these stripes. So that looks quite promising. Now, compared to the experiment, this is of course a highly simplified model. We have to include hydrodynamics. because that's the polymers are liquid. So this was a more generic phase separation situation where the evolution was just driven by diffusion. We have three constituents in the problem, two polymers and a solvent. So the situation here basically assumes the solvent is constant and only acts as a temperature that controls the bulk free energy. We have a free and deformable boundary instead of an upper wall. And once we've included all this, you might also want to look at the effect of shear flow imposed by the spinning, which can change the patterning quite significantly, both in this case as well as in the Marangoni instability situation. Thank you very much for your attention.
What determines the wavelengths of your pattern?
Well, there is no parameter anymore in this problem. So once you've done the lubrication theory, the length scale is order 1 essentially. Right. So that's the basic answer. You can, yes.
One on what scale? On the long scale or on the short scale?
It must be 1 on the long scale, of course.
You scale the contact angle to 1.
Yes.
To 1, and then the distance between the two plates goes with the, it's 45 degrees essentially.
Right. So we scaled h with the distance of the plates, but the lateral separation is scaled with the contact angle.
When it hits the wall, is essentially given by the geometry. The 45 degree to the distance of the wall gives you when it hits the next time.
Yes.
And I think one is the contact angle, but the other thing is that I think you showed when you have no wall on the top, then there is a length scale where where it ruptures. So you need to, with your height of your second plate, basically, you need to be lower than that.
Yeah, that's a secondary nucleation effect.
Yeah. So
Take away the upper plate, and you have this
Yes.
the dimple.
in fact, it's kind of buried in this contact angle.
When you compare the long wave model and the phase field model, the long wave model, what mobility did it have?
That had h to 0, so it's really the fourth order heat equation.
Right, so it's really both is just diffusive dynamics.
Yes.
So
Which
there's
is
no-
kind of surprising because we have Voigt diffusion in the problem, but that's what comes out of the lubrication theory in the end.
In your cantilever model, how have you chosen the diffusivity coefficient? I saw in your simulation with the phase separation to write this slide. It was an epsilon 0.03.
So this was not based now on a physical argument. So the idea is that once chi becomes order 1-ish sort of, and the equilibria of the free energy have separated to be plus minus 1, you want to have an interface which is small, because otherwise you can't do the sharp interface limit. So it has to be small compared to other length scale, and the only real other length scale you've got is the width of the channel. So it has to be, and the width of the channel is scaled to 1-ish sort of. So epsilon has to be small, so you get a sharp interface.
And how change the structure? So this type is the change.
As long as it's small enough, it shouldn't change anything, because that's what the sharp interface limit says.
Yeah.
Of course, if epsilon is 1/2 or 1, then you basically just get a blur. There's no real interface there anymore. Or if you stay close to the critical temperature, there's no interface. The effective width of the interface becomes very large, even for a fixed epsilon.
Mm. question? I have a last one. When you look just at the decomposition, I think it was the first part of the last part. You had first this binodal pattern everywhere, and then it settled to stripes that were, I think, vertical to the walls. So is it just a selection of your picture that you get it sometimes vertical, sometimes horizontal, or is there a symmetry breaking in the boundary conditions? Naturally they are periodic, right? And this one.
So what are you wondering about, the 90 degrees, or that you get vertical
why
stripes?
is it vertical and not horizontal?
I would have thought the fact that you get the horizontal one is the more surprising one, because this is the more stable situation. The interfaces are shorter, so the energy
But
should be...
it's a square, right?
Well,
Oh, no, wait, this is... oh, no, I see, yeah, okay. It's really the length scales.
Yes, I think
okay.
so.
Yeah, no, I see.
I mean, the point of this exercise was a simple Hilliard type model with the necessary elements of confinement and so on, and surface energies. What determines the formation of the bilates? Is it possible, first of all? This was our first question. And then under which conditions? So what do we see in the experiment? Can we get some information even from a simple model? And in a way it confirms that you need to have a slower method to obtain this metastatic bilate. Otherwise you get this.
Okay, so I propose we thank our speakers of today.